my voice will hold even an early lunch break. Conical coming over. So, I would like to tell you a little bit about Rydberg atoms moved by exciton-induced forces. So that was mentioned at some point already, that one can have hopping between dipole-dipole-induced transitions from one Rydberg atom to another one. And you will see that we will really focus in this kind of line of research on the fact that these dipole-dipole forces, they really exert mechanical force in the atoms. And by that one can transfer electronic excitation. And if one basically does not force these atoms to do something, but let the force act which is induced by the electronic excitation, then one can hope to preserve coherence as long as possible. That's kind of the idea, to explore that in the context of ultra-cold Rydberg gases, of course. And the guy who mostly is responsible for that work by now is Sebastian. He's really concerned with ultra-cold exciton dynamics. Alexander Eisfeld is a specialist on quantum aggregates in a more general context. You will hear about quantum aggregates also, of course, in these three lectures. Now, of course, you know Thomas very well, and we call him Mr. Rydberg in Dresden. And he's mainly concerned these days with the many-body interface of light and matter and ultra-cold gases. We've heard already about that. So I will talk about these two aspects. And this is kind of my personal perspective on that. Basically, the relation between ultra-cold Rydberg dynamics and atomic motion. We can look at many-body quantum interactions of light and matter. And you know, this is mainly a frozen gas. You can basically look at lattices of Rydberg atoms. You get phenomena like the interaction blockade, which has been instrumental to obtain very, very interesting results. Correlated dynamics and so on address single Rydberg atoms in the experiment, even an ensemble. Of course, EIT has proven to be very important and useful, even to come to something like almost single photon control. On the other side of this very quantum-like, quantum optics-like features, there's the ionization in a trapped gas. Let's say you have a trapped gas in your hot or whatever, and you ionize that. Very gently, if you wish, but after a while, your electrons don't get away anymore because you have this huge background ionic charge, and the electrons get trapped, and they form a plasma, an ultra-cold plasma. So this brings all of a sudden ultra-cold Rydberg gases into the regime of plasma physics, and some of you probably do that these days, also experimentally. And you can study now strongly coupled plasmas very easily in the lab. This has been very difficult so far. They only exist under extreme conditions, let's say in the sun or other stars and so on. It's not so easy to access. And of course, I think present interest is something like ion acoustic waves, so really already induced phenomena in these ultra-cold plasmas. And then there's might be something in between. This is molecular binding. You can have long-range molecules, very strange molecules, you probably know about them, where you excite one atom to a large Rydberg orbit, so large that another ground state atom is within this radius or circle of this Rydberg atom, and this forms then kind of a diatomic molecule with this ground state atom and the excited Rydberg electron in its ion. And this was proposed by Chris Green a while ago and by our German organizer, Hossein Sadakpour, is trilobite states, and I think Peter will talk about that more in one of the lectures. He just mentioned that this morning. And the other aspect I will address in this kind of molecular regime is really Rydberg aggregates, the transport of excitonic Rydberg excitation. Now, the question is, what do have these three regions of ultra-cold Rydberg phenomena to do with atomic motion? And I think here on the left-hand side, atomic motion is kind of a necessary side effect. It is temperature fluctuations, collisions. Essentially, you're not interested in that. You want to have the geometrical organization of your excited sites, and you want to have a frozen gas, and all the rest is kind of dirt. That's kind of the condensed matter aspect, if you wish. Now, for the plasma physics, the atomic, and that is in that case an ionic motion if you have ionized your gas, and the electronic motion are completely separated. In fact, we have two plasmas, the ionic plasma and the electronic plasma, and depending on the temperature, both of them, or at least one of them, is strongly coupled. And in between is, of course, this kind of what I would call chemistry aspect of Rydberg dynamics, ultra-cold Rydberg dynamics, this molecular binding, where the atomic motion is really a constitutional element, and it's really very intimately intertwined with the electron dynamics. Clearly, I mean, a bound molecule, you know that it stays coherent forever, right, in the ground state, and this is because the vibrational motion and the electronic motion are very, very intimately coupled in a very subtle sense, so that this kind of bound state comes into existence. Yeah, and you can also kind of view that as a scale from going from the deep quantum regime to the classical regime. This is really totally classical, these ultra-cold plasmas. And here in between, in this chemistry phenomena, we are in the semi-classical regime. I personally like semi-classics a lot. I think it's a very interesting theory one can do there. And exactly for that reason, Charles mentioned before that classical mechanics overburdens you with lots of nice nonlinear things, which are sometimes washed out in quantum mechanics, but which give very interesting structure to your problem. And today I will try to, get you a little bit of a feeling of many kind of semi-classical aspects one can have in also adiabatic motion and so on, not necessarily directly linked to your ultra-cold Rydberg atoms, but maybe hopefully useful for you one day. You'll remember that when you have a problem that there's some trick you can apply, which you might take home from here. So we will deal with this regime, as I said, the chemistry aspect, and especially, with the transport of excitonic Rydberg excitation. Now, why is this interesting or important? You all know, and this was also mentioned briefly already, I think, once here during the school, that excitonic transfer is really vital in the true sense of the word for us, for life, because it's very important in the process of converting light to energy in light harvesting complexes. And here are two of them, and we still don't really understand how this works. And therefore, like always in physics, it's nice to have a system which keeps the principle, but it's much simpler and can be much easier manipulated. So it's kind of much cleaner. And there, ultra-cold Rydberg systems hold this promise, at least to some extent. Here maybe you see a little comparison. So we have these molecular aggregates. We are interested in to understand the basis of life here. And they are, this was already mentioned, relatively small, like angstrom size distances. And also they are kind of fixed, and they have a protein environment. So the interaction with this environment is quite strong and makes kind of the phenomena we are interested in terms of this exciton transport, energy transport, difficult to understand because one never knows what is the pure mechanism and what is due to the environment, noise, fluctuations, and so on. On the other hand, if you can construct a Rydberg exciton chain, let's say, of atoms here, that's the easiest thing. I will more or less focus on that. We're just about to go beyond that, but not much. Then these Rydberg atoms are free to move in this one direction at least, if you have a trap which confines them in the other two. And they have very large distances, as you know, micrometers, depending of course on the excitation, that's the scale of the system. And the interaction with the environment is then by construction really weak. So we can study in a very pure way this excitonic transfer and transport along these chains. You can see it can be done, and can think later on making networks of the Rydberg atoms and see how different paths come from coherent or incoherent excitation transport. Yeah, so I think that's a general scheme you have probably witnessed and encountered in whatever area of ultra-cold Rydberg physics you work. This ultra-cold Rydberg dynamics is very, very nice to study in detail certain mechanisms which occur in other basically areas of physics, because you can kind of magnify the effect And that means you can really take it literally to larger scales. You can almost look at that then in the CCD camera, micrometers are accessible. And you can also magnify, quote-unquote, the time scale in the sense that you make it much, much slower. So you can also follow basically the dynamics in time. And this is also true in a way now here for the excitonic phenomena induced, of course, by dipole-dipole interactions in the micrometer regime. So what are the questions we should ask and hopefully partially answer? And of course, we are interested in transport of electronic excitation and coherence across many sites of atoms or molecules in the more general context. And we know that this transport is limited by decoherence mechanisms of various kinds. Important sources are atomic motion, phonons, and so on. And I alluded to that already a little bit. We have the observation that in a molecule, atomic, in this case the nuclei, and electronic motion are so intimately related that coherence is preserved in the ground state even indefinitely. So we would like to learn how this works, to copy it basically to the transport we're interested in. And of course, this is a very different system because it's a bound system and periodic. We want to really have directed motion. And so our next observation is that electronic Rydberg excitation exerts well-defined, almost localized mechanical forces on the atoms. And now the idea is really to use this force to naturally transport electronic excitation across an extended system and stay coherent as long as possible. Okay, so what concepts do we need to realize that? Essentially, we need two kinds of concepts. We need to address the aspect of the atomic motion, how the atoms move, and we need to address the aspect of the electronic dynamics excitation. So this kind of first part of the lecture today addresses the atomic part, the nuclear motion, and the basic description of molecular dynamics combines these two elements, the electronic and the nuclear motion, and you know you can separate it very well in terms of the Born-Oppenheimer approximation, and this relies on the fact that the nuclei are much heavier than the electrons, and therefore they move generally much slower than the electrons, and that allows you to adiabatically separate these two dynamics. And the more general concept of Born-Oppenheimer approximation is basically an adiabatic separation of slow variables and potential curves, and this we will discuss now a little bit. And of course, the prevalent phenomenon is avoided crossing. We just heard about that in detail from Tom Gallagher. And then, of course, how to get across an avoided crossing in terms of a diabatic passage. By the way, do you know what diabatic means? Does anybody have a Greek of you, ancient Greek? Diabane? Step over. Yeah, almost. Step through. Dia is through, yeah? So walk through, it means walk through. And A is always do not, right? So do not walk through is adiabatic. Yeah, and then of course, if you go multidimensional, you have the phenomenon of conical intersections, which are, again, extremely important for these light harvesting complexes in chemical systems which support biological functions. And just for the fun of it, I will introduce you to two little here off-the-road twists. One is the reflection principle in molecular dynamics. This is linked to a semi-classical approximation of the dynamics, which makes life very easy, gives you almost analytical results. And in modern times now, many colleagues use that basically under the term quantum fidelity. That means you propagate in one direction with one Hamiltonian time, and then you propagate backwards with a different Hamiltonian, slightly different, and you can make certain approximations to evaluate expectation values of this double propagation. And on this notion, the reflection principle in molecular physics is also based. And if time permits, I will tell you that we live in a world without time. This is kind of very topical here at the biosphere, right? and that you actually can construct time from space by adiabatic separation, in the adiabatic principle of your environment and your system you're interested in. We'll see if I come to that today, if not, we do tomorrow. Okay, what we then need as a second part, I said we need to address the electronic dynamics for our transport of excitation. This we will do mainly tomorrow. And that's of course the theory of electronic transport for fixed nuclei, and this is excitons. I will try to describe to you very briefly the general concept. It goes back to Frankel and Warnier and Mott, who kind of did the same type of excitons, and this was very early in 1931 and 1937. They found already this approach. And then I will specify that a little bit to what we need. This is molecular hooks, molecular aggregates. And we'll just discuss with you in detail the dimer as a minimal unit of an aggregate. An aggregate is simply a number of n identical species, big molecules, whatever you want, could be Rydberg atoms, doesn't matter, just identical, and they are coupled by the same type of interaction, whereas normally dipole-dipole interaction. Yeah, and then we will discuss how basically one kind of transitions between these units, transition moments, dipole-dipole coupling, also absorption, because that's mathematically very similar. We will generalize that to excitons in large systems, discuss linear J aggregates, that gets us already closer to our Rydberg atomic chain, and then switch to the exciton concept for atomic Rydberg aggregates, and maybe discuss, hopefully, then tomorrow as the last part, the first attempt to describe dynamics in a chain of Rydberg atoms, and in that case, only adiabatic dynamics. Okay, so what is adiabatic separation? As you know, it's most common for molecules where the electrons move fast because they're much lighter and the nuclei is low. So you separate the dynamics of these two basically coordinate systems. And a more general concept, also in few body dynamics, very popular, nuclear physics and so on, but also atomic physics, separates the hyperradius of a system from the hyperangles in the 3n-3 dimensional description of an n-particle system. And I tell you that so you realize that it's not really only von Oppenheimer molecules, so adiabatic is much more general, we probably know that. And it's not only related to fast and slow necessarily, it's really more related to the fact that you don't change the energy of your surface a lot, which is parameterized with your adiabatic parameter. This is the main concept. So here the idea is, why this works in most really few body systems, is that simply if you change the overall size of your system, then the energy does not change a lot on an adiabatic surface. That's the idea. While the internal degrees of freedom can be rearranged and certain energy losses in one coordinate can be compensated by energy gains in another one. So the overall energy at the same size of the system hyperradius does not change. And the hyperradius is simply then the geometrical radius of the sphere in 3 dimensions. And again, our organizer Hussein did that a long time ago. Here you see basically potential curves parameterized with the hyperradius of the system. And you see this is really a mess, like a big calculation. And this was for a very small system, H-. So basically 2 electrons, 1 proton. And that's all the excited states. And you see here on the right hand side, if you go to infinity with your hyperradius, that means one particle leaves, you're left with one electron goes away, let's say, you're left with a proton and an electron bound together or excited, that's hydrogen. And correspondingly, you would expect here hydrogen channels, so hydrogen energies. When you see here the energy is 2, 3, 4, 5, 6, and so on. And the reason is that Hussein chose a very clever parameterization of the energy, which is, of course, well adapted to the problem. If you go to high excitation, normally you know that the hydrogenic energy goes with -1/2 n squared. So this becomes denser and denser if you go to threshold. And here this is parameterized now with n. So we have here as a function of hyperradius, and make this as an effective quantum number n, and basically plot n of r instead of the energy, which is 2 times the energy and less than minus 1/2. So that's really the quantity which is plotted here, which gives you then a nice equidistant representation of your channels. But of course, we don't want to discuss H minus here, but what I wanted to show you that really it makes sense here to separate adiabatic in the hyperradius of the system. You see it's very well organized. We see that even better if you take only the lowest channel here in each of these manifolds. This is very systematic. And here you see now the vibrational energies. This is what you expect in typical Born-Oppenheimer type of approaches. You first calculate here the electronic eigenenergies as a function of the size of the system, and then set that the system basically breathe or vibrate. This gives you the total eigenenergies. Okay, so what do we learn? I mean, here it looks like that all these different curves have many, many crossings. In fact, they do not have a single crossing, they are all avoided crossings. And, oops, it's shown here, but it's right there. So, essentially, it says there's a Wigner von Neumann non-crossing rule, which says that if you have potential curves within the same symmetry class, and you have only a single adiabatic parameter, like here the hyperradius, then these potential curves cannot cross. And this we can understand relatively easily with the most simple model we can do. We just take 2 potential curves and see how they behave. And this is shown here. And probably you know that, maybe not, but this was basically alluded to so often already here. It's such a basic problem that I decided I just discuss that a little bit with you. So let's take now 2 potential curves, 2 channels, yeah? And without any perturbation, they are assumed to cross here. So the potential curve 1 is, just for simplicity, written here as basically a linear energy, let's say here. And the other one also as a linear energy, the next channel, but with a different slope. F1 and F2 are the slopes here. So they cross. And now you have a perturbation of your system, and the perturbation is an off-diagonal coupling, we all know, H12. And to make the whole, or keep the whole Hamiltonian Hermitian, H12 needs to be the same as H21 if it's real, or basically the complex conjugate if it's complex, but we keep it real here. So H12 and H21 are the same, essentially. And then you can diagonalize that very easily, right? And you get basically the new energies. So R12, F2 plus F1. And then, of course, you have a quadratic equation. You get 2 energies, it splits, and lower and higher energy with the square root here determinant. And you see very clearly that the potential curves cannot cross, because when you try to make them cross, that essentially you have to make it square root 0, then you see this is not 0, this is just your perturbation, so this will always be a finite value here. And this is why you get a gap, and essentially this you can, depending on your perturbation, of course view again as a Rabi frequency or just a coupling matrix element, whatever is in your actual problem. Now what is important is that, and this is, I want to emphasize it for you, and also you should keep that in mind, is that the character of the adiabatic wave function changes through the avoided crossing. So this one can see here quite nicely. We start out here, maybe I have that even here better. Yeah, genau. There it is. So we start out here, here with our adiabatic wave function, psi1, and this goes over here to psi1. Now, asymptotically far away from the avoided crossing, the diabatic and the adiabatic wave function, of course, agree. Yeah? But you see, you start out here diabatically with phi1, and this one is the other asymptote, this is phi2. So the adiabatic wave function psi1 changes its character at the avoided crossing, going from phi1 to phi2, and correspondingly the other adiabatic channel coming from phi2 to phi1. This is psi2. And that's very important. This is kind of the Adiabatic Theorem, which is spelled out here again. And it says essentially that a slow change of the adiabatic parameter R allows the system to adjust and change its wave function psi adiabatically to keep the energy change minimal along the potential curve. Yeah? And this is what I just told you. So you go really here from this channel, phi1, with your adiabatic wave function psi1, into the other one, phi2, with one adiabatic wave function. And you see the energy change, of course, is smaller going along this adiabat as compared to the diabat, where the energy change is much larger. So this gives you the other possibility. If the system is such that the adiabatic parameter is transversed very fast through some system property, then this does not allow for an adjustment of the wave function, and you actually get a diabatic passage. And essentially, this keeps the character of the wave function, phi1. But of course, you pay with the energy. The energy changes much more. So these are the two kind of complementary possibilities, adiabatic or diabatic passage of an avoided crossing. And now, of course, the question comes up, what's the probability for a diabatic passage? So how likely is it that I actually jump from one adiabatic surface to the other one here? And this was answered independently by Landa and Zener, also a long time ago. But this is mathematically not so easy actually to derive. And only in 2005, and I can recommend this paper, it's kind of nicely written, there was kind of a new derivation, which is by complex contour integration, which makes it much clearer what goes on. And the result is essentially that the probability for a diabatic passage is exponentially damped. It's e to the minus 2 pi times basically here a frequency. And the frequency is nothing but the coupling matrix element over h bar times the time it takes to pass this avoided crossing. And this time to pass the avoided crossing is now the tricky part. I think this, of course, is a very reasonable expression. You probably would come up by yourself and think a little bit about it. But what the actual parameters are, which define then this diabatic time, is not so easy to derive. And what it actually is, you can think of it as the characteristic length of the passage divided by the velocity with which you pass basically the avoided crossing. And the length you can simply define again by the energy of the gap. This is the coupling matrix element. This would be basically the gap at the avoided crossing here, h12, that's an energy, divided by the difference of the slopes of the two curves. Oops. Yeah. So this is then a length because, I mean, the slopes of the two curves, of course, is an energy derivative with respect to a length. So divided by energy over length gives you a total length. And now the velocity is simply how fast you change your adiabatic parameter here. That's of course an external thing. So this is not necessarily given in the dynamics. This depends how your system basically behaves and how fast you pass this avoided crossing. But that tells you then essentially how likely it is to jump on the other channel to make really a diabatic transition instead of following your adiabatic curve. Okay. And the question is now, when can potential curves actually really cross? Because right now we always had avoided crossings and we have a certain likelihood that you can jump across the avoided crossing. Yeah? But the basic curves really are avoiding each other. Now, if channels belong to different symmetries, such that coupling matrix element, such that the coupling matrix element is necessarily zero, then of course they can cross. And the other point is, right now we have been talking only about a scalar adiabatic parameter, one-dimensional. But of course, in a polyatomic molecule and other systems, you can have multidimensional adiabatic parameters. So instead of a scalar, a vector. And then, in general, these adiabatic potentials can cross. This actually is then the phenomenon of a conical intersection, which is very far spread in chemical systems. That's actually the normal situation. And to understand that a little bit, we go back to our very simple system of two channels and discuss now how we can actually see that these two channels can cross once we make out of the scalar adiabatic parameter a vector. So how can that happen? I will try to illustrate that to you on the blackboard, or better the whiteboard. Wow. Thanks. Provide light and lightness. Yeah, thanks, Charles. So in general, we have multi-dimensional adiabatic parameter. Yeah? So R goes over to really a vector of R. And then we simply take the same situation here. So that is, we take our already diagonalized curves, but we write them in general with the U's. So E plus minus, two channels, is then U1 of R plus U2 of R by 1/2 plus minus U1 of R minus U2 of R by 1/2 squared plus the coupling matrix element squared, and that's again, of course, your square root. Now the question is, again, for getting degeneracy, we want to have at some R0, yeah, vector, some value of the adiabatic multidimensional vector. We want to have that A plus of R0 equals A minus of R0. So this needs to be proven. What do we need for that? Well, what we need is, we need to simultaneously have, and now I should say, of course, we make this also in general R dependent. That's the general situation. So what we need to fulfill that simultaneously the whole square root vanishes, right? That means that we need U1 of R plus U2 of R, that we define as one function of R equals 0, and we need that H12 of R, you can just define it as another abstract function of your adiabatic parameter, needs also to be 0, and that means at the same point. And now you see why a scalar parameter is not sufficient to do that. We have two conditions, yeah, which need to be fulfilled, two equations. Of course, we find a certain R0, which fulfills that one. And if it's a vector that fixes only one component of our R0, therefore we can certainly fulfill with the same vector than this other condition. And that means essentially then we have a crossing. While in one dimension, we would exhaust basically all our possibilities, fixing the scalar R with one of these two conditions, which will never allow us to get a degeneracy. And therefore, the crossing remains avoided after diagonalization. Now, what this gives you then, in the end, is something like that, famous conical intersection. So now we have essentially a two-dimensional parameter plane, minimal, so that's, let's say, Rx and Ry. Here's our energy of R vector, and essentially at some point here we have this crossing of the potential curves, and it's really here this kind of geometry. And this, of course, is very important, as I said again, in many chemical systems, because if you have a vanishing gap, you can imagine it can have very fast transverse of one adiabatic surface to another one through a conical intersection, since there's no gap anymore. So this allows you these very fast, radiation-less transitions, which are so important in biological systems. Okay. So this is maybe summarized a little bit here. So for a molecule, this means we need at least 3 atoms, which are degenerate at one nuclear configuration. And these 3 atoms then span a plane, yeah, that can be parameterized by 2 coordinates, let's say Rx and Ry. And that's exactly the situation where you can encounter a conical intersection, kind of the minimal number of atoms necessary, a triatomic molecule, let's say. As I said already, these conical intersections are very important in the chemistry of biological systems, since they allow fast radiation-less de-excitation of electrons. Light harvesting complexes are the prime example, but also repair of UV radiation damage in DNA works via this mechanism. And of course, we will be interested, not today, but in another lecture, in the question, do conical intersections also play a role in Untitled Rydberg gases? Okay, and now already come, I think, to the 2 off-road twists, which do not have to do so much with ultra-cold Rydberg gases, although the reflection principle, and this is why I thought about presenting that to you, will be used by Thomas Pohl in one of his applications for ultra-cold Rydberg dynamics in the next lecture, and therefore I think it makes sense to tell you about that. Okay, so what is that? So this is now, again, a bit more blackboard work. It's all analytical. What you see here is the photoabsorption cross-section for a system. So that's kind of linear response theory. And you might recognize here essentially your Fermi's golden rule. You start from an initial state, make a dipole absorption, and go then to the final state. But this is the time-dependent version of it. And of course you sum over all final states at a certain photon frequency, because you have the total photoabsorption cross-section.